first, I would like to express my gratitude to the Amran Society for inviting me here. It's a very humbling experience to be with such distinguished speakers with today's panels, even yesterday's. So thank you for that. As our moderator has announced, the discussion today is on the impact of emergency preparedness in terms of design. The emergency preparedness cycle obviously is a well-developed cycle. So what we've done with this paper is that we've gone over the requirement of emergency preparedness for a hospital and kind of highlighted the requirements or the impact of that on the designs. What can we do now while we are designing, as opposed to waiting later and doing it later to have our hospital prepared? So things that are very easy, very cost effective, which we can start with right now. Now, obviously, if your hospital is one of the new hospitals being built newly, you may not have much of a problem in terms of incorporating these elements. But if you've had maybe an older version of the designs, you may still need to go and take a look on some of those elements. So we will discuss, obviously, the need of emergency preparedness. What does emergency management mean in terms of phases? A little bit of principles on hierarchy of control, especially for controlling hazards. This is an industrial hygiene kind of table. A little bit more of emergency. What do we need to be prepared for in terms of emergencies? Why do people need to be prepared for emergencies? And a little bit of suggested items. Obviously, we will discuss a principle of kind of listing all of your vulnerabilities and being able to mitigate those in a design. We've seen one of the greatest enemy of emergency preparedness is what we call complacency, which means this is not going to happen to me. So it's going to happen to someone else. This is the biggest enemy of an emergency management system. When you do not accept that there may be an emergency which will come to your hospital. So just be aware of that. We've all seen examples here in the regions. We're not going to dwell too much on those. And some of the incidents that happened close to home. I mean, it's not something you hear on CNN. It's here. It's close to home. We've seen a little bit of fires. I'm not going to go into this because they're all sad stories, obviously. Evacuations in hospitals. Flooded hospitals, obviously. That makes you think about putting all radiology in your basements if you're below the floodplain. Little bit. This is in Emirates, where I'm based. So let's talk about the emergency management. It does have three phases. Obviously, one meaning mitigations, which is to be able to identify all of your risks and what kind of measures you're able to kind of exercise to reduce the risk of your, to reduce the impact of your risk. Preparedness being the second, response and recovery. In our case right now, we're at the mitigation level. This is why this discussion is happening, because we are still designing the facility right now. And obviously, in part of definitions, the reason I've just included this is because later on, when you have the presentations, it can maybe help as a reference to everyone. So by mitigations, we mean that we need to reduce the loss on the facility, on our system, before it actually happens. So these are pre-incident type of things. Being preparedness is a continuous cycle. Once you have your facility up and running, being prepared is ongoing all the time. Whether it's by training, having the right equipment, having the right policies, the right plans. We're not going to dwell too much on this, but there are plans that are requirements. The requirement of these plans in terms of designs is what's incorporated over here. This is the response. Again, there are elements of the response that's required, and we can see from the picture, there is at least one room where everyone sits to be able to manage the incident, which is what we call the incident command center. And recovery going back to normal. In terms of hierarchy of control, obviously, we're looking at elimination being the first one to eliminate the risk all the way down to PPE. For our discussion today, we're looking at engineering. So the emergency management cycle will have 4 phases, mitigation being the first, preparedness the second, and put on that this layer, which is engineering. So the first thing we need to do to be prepared is to use the engineering elements to help us be ready for the emergency. Just some concepts, because you're going to hear this. We're not going to dwell too much into details. These are just for your references later. There is what we call an emergency operation plan for every facility. It has all the elements that's required during operations to actually start activities. Who's responsible, what are they responsible for, and so forth. Some of the examples of the emergencies obviously are things that are beyond our controls, say like earthquakes and tsunamis and tornadoes. Some could be ours also, but these are external. External meaning it comes from outside the facility, so not from the inside of the facility. It's important to understand these risks, because as we said in mitigations, we have to have all of our risks written down. What have the area where our hospital is located, have it been exposed to historically, statistically? We have to do all of this. And this is where I call for cooperations between hospitals among themselves. If they're located in the same region, sit together and jot down all of these risks so you can start working on a common ground in terms of mitigation. Sea burn, water disruptions, and so forth. These are some of the internal emergency. Hazardous material skills, obviously, I mean, these are operations. You have your spill kits, infant abductions, loss of water, so on and so forth. Now, this is just for reference. For more information, where you can go and get. Why do people need to be ready? Right now, it's also becoming part of accreditation. So if you are, these are the motivating factors, obviously. If you are working in Saudi Arabia and you're going to have your facility operating here, you're probably going to have to abide by, say, Sibahi, which do have emergency management elements within their own guidelines. We're expecting the new guidelines to be published, I think, in March for the facility design and for the operationals, so those will only be enforced there. Legislation is another, so maybe your authority, your regulator will say, I need you to be prepared for the emergency and so forth. Another accreditation system is obviously ACHS. I'm just going to go through all of this because these are all operationals, but I just wanted to show you some of the pictures, some of the things that we will need. And move on to this is the emergency requirements in terms of medical equipment. Now we'll start with the suggested designs. And we said these are all engineering controls. First one is what we call the HVAC intakes, guarding your intakes. Suppose your hospital is close to an industrial facility inland, or your facility is close to a seaport where they transport chemicals, or to a highway, or where a train transports hazardous material, and there has been a spillage of that. Then you have a toxic cloud. You may have a toxic cloud coming into your systems. That's going to go into your HVAC systems, okay? So if informed, what can you do in terms of engineering to protect the ventilation of your system? This is where we recommend that as engineering, as a facility manager, you should have, from the design point of view, a flip of a switch to say, okay, now my system is closed. I no longer take ventilations out of the normal intakes, and I can at least until the toxic cloud passes. So these are simple engineering requirements. Another requirement would be the decontamination. Again, same scenarios. Your hospital is close to an industrial area where they deal with chemicals, and you have a spill, and you have 12 cases of contaminated patients coming in. You cannot allow those patients to go up past your ER, not even into your ER. Now, obviously, if you're a newly designed hospital, you will have your own internal decontamination area whereby you will clean those patients before taking them into your medical facility. But what if it's more than your capacity in terms of your internal decontamination areas? What do you do then? This is where it's suggested that to turn some of the areas just outside your ER, like your ambulance bays, your parking spaces very close, into external decontamination areas. In terms of equipment, those are easy. We can buy the prop-up tents, we can hook up the water supplies, but we need places to hook up all of these utilities. So making the provisions from the beginning to have your water supply, your special drain, electrical supply, and a few of the other considerations at the time of design would be helpful. So this is where we say, this is going to be my allocated space to put my prop-ups. And then you can tell your emergency services, I can take 15 people, I can take 20 people an hour, or whatever the number is. Just to highlight some of the elements here, we need to look at especially the hazardous material. Remember, once you wash and decontaminate a patient, that water becomes hazardous. So you're no longer able to put it into the sewage. It goes to a special tank. That tank needs to have access for a tanker to come and pull that material and treat it within norms. So again, very simple recommendation, and that is just to be ready for it. Building flush outs. Suppose now the emergency is actually from internal. Someone comes up with anthrax and slams it on the floor, and then you have a contaminated ward. Or someone comes up with, say, SARS into your emergency, and they're contaminated. What do you do? This is the ability to be able to either locate that area and flush out your system. So you don't want for instance, your anthrax or whatever biological agent they're using to be circulated within the system. So you just flush it out. All fresh air, everything goes out until your sensors tells you it's clear to go. Very close to the LEED requirements when you're flushing after construction, by the way. HVAC control. In every ward, we have maybe 1 isolation rooms, 2 isolation rooms. But what if, for instance, your hospital is next to a seaport, there's a cruise ship coming in, and they have 30 infected people you need to put in isolation? What do? Okay, you can go to those expensive equipment, $10,000, $15,000, you hook it up to your ventilation, and the whole thing turns into, with a HEPA filter, obviously, the whole thing turns into an isolation area. That's probably $10,000, $15,000. For a 30 ward, you're looking at $450,000 up to $450,000 to turn all of your ward into isolation. Whereas if you tell your MEP engineers from the beginning, I want to have the ability with a flip of a switch to turn this whole ward into an isolation ward, they can do it for you for a fraction of that price. Simple measures. If you have BMS, it's even easier. Same thing goes with the emergency department, because the emergency department is the first entry point where people are triaged. If they are contagious, obviously your nurse is going to pick it up. If not, you may need to isolate the whole ER. Incident command center, depending where you are, suppose you're a level 1 trauma center, or maybe you're a level 3, or you're just one on the network. I'm not sure how the system works here in the Saudi, in the kingdom. However, if, for instance, in the future we want to develop our trauma, and the government says instead of building trauma centers everywhere to the private sector, listen, we can allocate the trauma label designation for you if you abide by these rules, and then you may be within that network as a part of response. Whenever there is an emergency, we said we need to be prepared. There is an incident command, there is an incident commander, you can say. So those people who are managing the incident will need a place to sit, to communicate. They need power all the time. So this is where a command center will be allocated strategically within the facility to be able to redirect your resources within the facility and from the outside. So the command center will liaise with the civil defense, with the military, with the other hospitals. So you need communication. And in emergency, as we've all learned, you cannot rely on your mobile phones and push to talk and all of these. You need two-way radios, you need shortwave radios, you need ham radios, and all of this, they need antennas. They could be on the roofs with redundant antennas. So if you're sitting on the ground level, you can't use a satellite phone. You need a place to hook up your satellite with an antenna. Simple solutions, so properly sized cables with the right impedance will work. Again, think of these requirements in terms of incident command center. Usually there is a spokesman for the hospital to relay some message when there is an emergency, a huge number of deaths, let's say, or injuries, something that captures the media attention. You have to deal with the media. You can't say, this is not my problem, let them figure out what's going on. At some point, a spokesperson is going to have to come out and provide a release. So maybe a small press room where reporters can hook up to internet, get some power for their phones, their PDAs, and their computers. Or it could be just external, like in this picture, but the cabling will be their requirements. Disaster lockers and storage. When we initiate the plan, we've identified the emergency. The incident commander have scaled the emergency according to its risk level or hazard level, And now we've identified who's on board of this emergency. Maybe we're getting extra surge of, more than a surge of emergency patients coming in, or maybe it's internal. It doesn't matter. There are teams which needs to report to their stations with their own supplies. If you standardize, so they all have kits, they all have supplies. If you take it as a concept to say, okay, in every ward or in every department, I'm going to put my disaster locker behind, say, the main door of that department. Then if I am an employee of that hospital and I'm anywhere in that hospital, I know where disaster supplies are. So I don't have to look for them. I don't have to go to the equipment room and look for a huge duffel bag for an emergency supply. It's just one place across the whole facility. It's standard. Reinforced windows. In places where you have, for instance, tornadoes or you have debris, tornado winds, you have debris, things that are flying that slams into your windows and break them. Consider reinforcing windows, especially at the lower levels where the heavy items will be mobilized. Additional power. The electrical company tells you, okay, we have an emergency, we're going to have a shutdown for more than 3 days, possibly 7 days. What are you going to do? You need to have the ability as a facility manager to bring in more generators. You already have your generators, they're working, it's great, but they don't work 100%. I mean, unless you've put the money to get your generators at that level. You need to get more generators to the hospital either by renting them or what have you. Once they come, you need to have the ability to hook up your generators directly into your system without any rewiring. So all it needs is a nice switch gear that sits there connected to your system, a place where the generators are going to sit with the fuel line ready to go. Water controls. What if your a water main breaks into your facility? Do you know where the valves are? In terms of design, it's very important for the MEP to identify where the main valves are, how to access them, and make it very clear as part of also wayfinding for the technical staff. Where is the main valve shut down? By the time you call the authorities to come and help you shut down onto your zone, the damage will be too great. Security. People, depending on the system, obviously, whenever we have some sort of an emergency on a bigger scale, people need to go somewhere into shelters. Sometimes they are hospitals, sports clubs, but the first thing that's going to come to mind where people to go for shelter, for safety, is going to be your hospital. So if you have an area where you have a huge displaced population, the first thing they're going to do is to come to you as a hospital. So are you able to accommodate them in your landscaping areas, into your parking areas? And if so, you obviously need security just to make sure they're okay until the authority comes and relocates them into some other areas. Air transportations. Whenever we size a helipad, you size it according to some assumption. And obviously, not all helicopters are created equal. The weight plays a factor, and the rotors plays a factor. So what if your helipad, say, is on top of a building or designed for a smaller helicopter, but the big guns are really helping you? You know, the military was called in, or the Air Force was called in to help with your incident response. Can those huge helicopters really land on your helipads? Medical air, now we're going into systems as opposed to facilities. Same thing, quick connect for additional compressors. Okay, you do have your cylinder full manifolds ready with all the cylinders, but even still, if you need to bring in an additional air compressor, you have a quick connect, you can just hook it up into your systems and you're getting that additional air. Same thing goes with oxygens. Although oxygen is was more of a security concern because of its explosive nature. Again, this is you have to be ready for this as an emergency. I'm just throwing this in because this is of interest to the healthcare regulators or people who are in the system. This is a beautiful document that was released, I think it was December of last year. And it's a tool to actually help you assess the readiness of the whole healthcare systems. Identifying some of the elements there may also identify some of the things that will have impact on design. And thank you. I think I've made my time.
Thank you very much.
Okay.
Our next presenter is Graham Robertson.
Firstly, if we consider the key elements of an intelligent infrastructure, these would be the power infrastructure, all the electricity in the hospital, the heating, ventilation, air conditioning controls and management systems, the integrated security systems, lighting control, specialist systems for medical wards, and life safety systems, together with the IT data center server rooms and operating theatres. A complete system of enterprise management links these various systems together, and if we consider those systems as centres of intelligence, what in effect this new design philosophy does is it allows these centres of intelligence to connect with each other, and it basically gives the hospital or medical city a bigger brain and a bigger ability to function intelligently. Some of the key technologies amongst many that are affected by this are things like visitor management, the complete patient healing environment, the infection control systems, the noise monitoring systems, and other staff support systems. And the way that these systems interoperate is through using open international standard protocols where the various systems start to share information with one another, and they enable many, many more intelligent strategies and actions carried out by the building and its operators. Our organisation has developed hundreds of these, and we'd just like to share one or two with you to give you a flavour of this. One of the very important aspects in a hospital is to protect infants, obviously, and we saw a great presentation yesterday from our colleague in infant development. So infant protection systems can function intelligently to integrate access control, to shut off whole areas, to notify nursing staff and facilities and security personnel, to activate beacons, sounders, alarms, to go on to high-resolution video recording and enable a crisis command centre to be set up on an infant abduction. So processes are in place to deal with this. Another form of integration is life safety. So if a life safety event was to occur in the hospital, like a fire alarm, the intelligent infrastructure can function to activate access control, to allow exit through certain areas, to notify key personnel within the hospital, to activate the ventilation systems to prevent the spread of fire and smoke and to clear smoke from certain areas. Also to activate other facilities management systems and asset management systems to identify vulnerable patients, need to be moved, and all those things. The patient rooms themselves can be much more intelligent with this design. The patient rooms can be managed through bed management systems. The various infection control technologies can be integrated into a complete system, and the whole patient healing environment, including the environmental conditions, the amount of natural light the patients receive, and giving patients the facility to alter their own environment, to connect with social media, to be in touch with their families. And one final example is the operating rooms, a very vital area of any hospital, so that operating theatres can be scheduled to fit the environmental conditions with the various procedures to be carried out. So the surgeon walks into the operating theatre and it's already at the optimum conditions for that procedure, allowing more efficiency. The control of the ventilation, air conditioning systems, lighting, and power management, as well as security, can be integrated to make the operating theatre a miniature intelligent building. Asset management, another enormously accelerating field in hospitals to manage assets. One simple example could be a maintenance engineer carrying out some maintenance activities. Staff can be identified that the equipment is under maintenance, badges can be printed in advance for the engineer, and access to various areas of the hospital that they will require, all functioning automatically to allow the maintenance to be carried out efficiently and more quickly than it is normally done. So with this type of sophistication, it's vital that human interaction is considered in the design. So the various physical systems are connected to an integrated management system providing graphical user interfaces for the various stakeholders within the hospital. So the skilled stakeholders such as security management, energy management, facilities management, and data center IT management, some operational interfaces for fire personnel, nurses stations, medical staff, surgeons panels, and facilities for the patients themselves to interact with the building in a way that supports their recovery. And of course, not to forget the management of the hospital. The hospital management can easily view all the key performance indicators of the hospital to help them manage this facility more effectively. The healing environment, there's many things that an intelligent infrastructure can do within the healing environment. And one of the most important areas is to improve infection control. Airborne infections are present in all hospitals, mainly due to the build-up of bacteria and pathogens on cooling coils. Even as we sit here today, we're probably breathing in a few germs. These pathogens build a film over the cooling coil which prevents airflow, and then eventually the bacteria and spores travel through the ductwork into the hospital and then basically into the lungs of patients and staff. And this is one of the main reasons why infections can spread within hospitals. A solution involving the use of ultraviolet light can be used to integrate with the intelligent infrastructure to eliminate the bacteria, to reduce pathogens by 99%, but also by eliminating the bacteria, we get rid of the film on the coils, and when we integrate this with intelligent inverter motor control and volumetric advanced air system control, we can actually increase the efficiency of these cooling coils by 77%, which then saves money and improves the sustainability of the hospital. One case study for this is the Prince Charles Hospital in Queensland, Australia, where the installation of UVC paid back within 15 months only based on energy saving alone. And that's not even taking into consideration the reduction in infection and the reduction in the average length of stay in the hospital. The UVC results, just to make you aware, those were some of the plates taken from the study. So on the left-hand side is probably, we might be breathing in that air now, so hope that doesn't make you feel any worse. Automatic hand hygiene monitoring systems, another very important area where a carer washes their hands with the required cleaning fluid, places their hands underneath a detection device which detects whether or not there is enough cleaning fluid on the hands. To make it doubly sure, a bedside device detects the cleaning fluid on the carer's hands from the bedside, so as the carer approaches the patient, if the carer has not put enough cleaning fluid on their hands, or they've touched something else, or it's evaporated, then their badge will illuminate, have an audible alarm and vibrate, and they have to return to clean their hands. Obviously, this will generate an alarm and a non-compliance record within the management system. This type of technology has been able to reduce hospital-acquired infections by 67%. One case study is the Miami Children's Hospital in the United States, where they achieved a 1,000% increase in observations because they weren't really observing this or recording it before. Compliance was over 90% during all the working shifts, including the night shift. And the 67% reduction included some reductions like urinary tract infections of 100%. Those were eliminated even after 3 years. An effect known as the Hawthorne effect is one of the reasons why these things are successful. And this is basically the tendency to perform or perceive differently when one knows one is being observed. And this really began back in the United States, back in the 1930s, with the first time and motion studies in the automotive and other manufacturing industries. Another good form of infection control is automatic flushing systems, which is a combination of intelligent valve technology and pressure control, which eliminates the possibility of the build-up of Legionella in the water systems. A couple of case studies. There was a bad outbreak in the UK at Liverpool Broadgreen Hospital. They installed the system, which managed to achieve a 40% reduction in Legionella. And then a further ongoing pilot study is underway at the Manchester Royal Infirmary, where so far no Legionella has been detected due to the installation in a new hospital building. So we feel this is very important. And another benefit of this is it actually saves water. So instead of manually flushing the cold water systems, this can be done automatically only when necessary, saving a lot of water, a lot of cost, and also manual operations. On a 500-bed hospital on average, you would save up to 200,000 manual flushing operations simply by the installation of this technology. So the intelligent infrastructure design philosophy integrates these forms of infection control and then provides a user-friendly touchscreen staff interface so that the staff can manage this on an individual, ward and departmental basis. By the same token, patient microclimate can be managed, so all the conditions that affect the patient, their well-being, the environment, their ability to change their environment, their access to social media to communicate with friends, family, relatives, and even the noise levels that they are experiencing can be monitored and controlled. One case study of climate control was at the Gateway Medical Centre in Clarksville, United States, where simply by controlling the level and increasing the level of natural light available to patients resulted in a 20% less pain medication costs, and also had the effect of reducing the average length of stay, which, as most of you, all of you probably know, has a big effect on the operating costs of a hospital. Noise and sleep fragmentation. Hospitals have become noisier places. The Johns Hopkins Hospital did some studies, and in the last 50 years, they've basically become 50% noisier due to the increased intensity of equipment around the hospital, causing sleep fragmentation with these ill effects with oxygen saturation, blood pressure effects, and respiratory problems, which affects the healing. And as we can see in this study, it affects individuals differently. So an increase of 20 decibels in the noise level will cause a sharp increase of sleep fragmentation and probability of arousal in certain types of vulnerable patients. One solution to this is to implement a system of noise monitoring using easily identifiable signs within the hospital which can clearly tell everyone when noise levels are acceptable, borderline, or unacceptable. And measures can be taken when they are unacceptable as part of the operating procedure of the hospital. One case study was carried out at the Royal Brisbane and Women's Hospital, where a noise monitoring and control system of 1.5 hours per day, where basically patients would have to wear headphones, staff movement was limited to only necessary movements, visitors were restricted for that period. This resulted in a 50% reduction in noise levels, with patients twice as likely to gain undisturbed sleep, obviously therefore having a positive effect on their blood pressure, physical experiences of pain, and on their emotional well-being, which are all important to aid a speedy recovery. Energy is a very important aspect, and energy costs throughout the world are rising, and they are becoming an increasingly important part of a hospital's operating costs. So ourselves, we have conducted a number of projects where we have used elements of an intelligent infrastructure to reduce the energy consumption in hospitals. This chain of private hospitals in Spain implemented efficient lighting, power, heating, ventilation controls, and enterprise management with extensive sub-metering, and achieved a 17% in their energy saving and a 20% cost saving of the installation of the systems. Another more extensive project in Sweden involving 3 very large hospitals took it a stage further to include, amongst the previous measures, also water conservation measures and a performance assurance, where our organisation assured them of the savings in such a way where if the savings were not achieved, then they would be refunded the difference in money. Such was the confidence to achieve these savings. The savings that were achieved were quite substantial, and this particular project was classified as an example of best practice by the European community. Plus, overall water savings of 56,000 cubic metres per year were also achieved by the water conservation measures. You may be wondering about the possible cost of such a technology infrastructure. So we carried out some studies on a project of ours in Texas, the Flower Mound Hospital, where we added the conservation measures and some additional technology integration of elevator management and bed management. And this actually resulted in a 12% saving in the capital cost due to material and labour efficiencies. So the message here is quite clear that although you will receive tremendous benefits from this type of design, it can, in some cases, result in a reduced cost as well. One of the areas where cost saving was achieved and project performance was improved was in creating an integrated project delivery mechanism where the traditional systems of multiple packages and discrete systems with overlapping project management and duplication were removed and replaced with an integrated, streamlined structure where a single point of contact could be provided and efficiencies could be achieved in the installation and installation management processes. One of the most highly energy-consuming parts of any hospital, with the exception of the kitchen, is of course the server rooms and data centres. And employing the very, very best of design and technology can result in a much reduced energy consumption of up to 30%. This involves the use of in-row cooling, so instead of cooling the whole room, you just bring cool air in and cool the servers, and then recover some of that heat to save energy. This type of design, as we can see here, creates a different thermodynamic pattern within the room, which results in a reduced footplate. So you can design the hospitals with more efficient, energy-efficient data centres, more scalable, and actually from an architectural point of view, I know there's lots of architects here, you can reduce the footprint of those server rooms at the same time. Now, we've lots of evidence about saving energy in existing hospitals, but what about new hospitals? What about hospitals that have not been designed yet? So we have conducted a pilot study based in hospitals in different climatic regions, using energy modelling, the latest energy modelling tools, dynamic simulation, from a standard to an integrated design. Our pilot study was a basic 400-bed hospital, and we implemented a range of measures, as you can see there, and entered those measures into the model and rerun the complete model for the year. The results were very encouraging. So the traditional design provided consumption of 43,000 megawatt hours per year, and the advanced design came up with a figure of 29,000 megawatt hours per year, a significant saving of 32%. So this type of design philosophy will result in increased sustainability and energy savings. Where some of the savings came from were in the lighting, the basic gas consumption, and in electricity consumption. So what this leads to for the future is a holistic infrastructure model where all the departments in the hospital can employ these technologies to have patient tracking and allow the facility to play a greater role in this process. So different departments with different KPIs can be integrated into a central system, which can be managed through a data centre. Data from doctors' surgeries can then be brought into the system, and the addition and development of telecare and remote services can also be provided. When we want to design these types of facilities and employ this design philosophy, it's very important that we try to develop and evolve away from some of the more traditional construction processes and go towards a more integrated project delivery process where specialist companies and specialists can be brought into the design process at an early stage, and these changes and developments can be introduced into the design. So in summary, we would strongly recommend that in all your projects, and we must say at this point that some of the most prestigious, largest and leading healthcare projects around the world are already implementing this type of philosophy, that it will improve your patient care, it will help to improve your staff productivity, it will improve adaptability and future-proofing of the facility, which is recommended by the World Health Organization, reduce your life cycle costs, and again, reduce waste. Again, the World Health Organization has identified that 20% of all money spent on healthcare is wasted. So, with that, I thank you very much for your kind attention. Thank you very much.
Thank you, Graham. Our next speaker this morning is Professor Ahmed Sharif. He is a professor of architecture at the American University in Cairo.
I wear two hats. I am a university professor who teaches architecture at the American University in Cairo. And I'm also a practitioner who is very much interested in hospital planning and design. Actually, I had engagements with the Ministry of Health here in several hospital projects. Today, I'm going to wear the hat of a university professor, so it's more about research, results of what we call evidence-based design, a topic that was introduced to us yesterday, and we show also some case studies today to show evidence that our design decisions should be based on evidence, not just about intuition or general concepts. So we are here investigating one specific aspect of hospital design. We took a very close look, a microscopic look on one of the rooms of the hospital, but it's a very important room, operating room. And we looked at the finished materials of such a room to see whether the decisions by designers were complying with actual practice, or actual practice was different from expectations of designers. So I will start with an overview from literature, from references about how building components like building surfaces, walls, floors, and ceiling can affect the performance of hospitals, and then move on onto the results of the study that you have performed. One of the references talked about that hospital design and construction materials have a considerable effect on both the environment and patients' health. Physical, contextual, and organizational aspects sets the stage for the majority of errors in healthcare settings. Materials selected in finishing of the surfaces of operating rooms specifically can have effect on performance. They must be suitable and supportive to the functions of these specialized spaces. They must withstand the various demands resulting from intensive use. Another reference talked about the benefits of molding design of a hospital to satisfy infection control principles. These will have an effect that typically lasts. It was observed that the effect of our decisions will typically last for 30 years. Wrong decisions are difficult and costly to rectify. A major study by one of the main authors of publications in healthcare design, Ehrlich, talked about that the literature supports the effectiveness of choosing easy to clean wall finishes as means of control of cross-infection. But they noted very much in that very important study efforts that evaluate and comprehensively compare the wall finishes based on performance criteria like infection control are very little. So we are here adding a little bit new information. Another reference talked about hospital operating rooms being the most profitable spaces in the hospitals, most profitable procedures. A properly designed operating room should contribute to efficient operation, prevent unnecessary costs, and mitigate injury to patients and staff. One last reference, environmental surfaces are one of the factors that contribute to the risk of contamination in operating rooms. In a recent study about views of facility managers. In a hospital setup, we do have the designer who designed the hospital, and then we do have also the managers or the facility managers who do run the hospitals in terms of operation maintenance, who observe the actual performance of the decisions of the designers. Facility managers in an important study identified various aspects that we will detail later on related to the that will affect the performance of a healthcare facility. One late study, 2012, last year in Texas, they identified 3 important criteria for decisions regarding surgical suite walls only, the walls of operating rooms, infection control and gas emission, indoor air quality, ease of maintenance and sound resistance, and then durability, cost of maintenance, other factors were ranked. That's in Texas. So we posed questions. We said, what are the factors that influence the performance of operating room finishes? What is the performance in use of the most commonly used finishes in regards to these factors? And then the last question was, did designer's material selection result in good performance as perceived by facility managers or not? So let us see what happened. So what we did do, we looked at 86 hospitals, a total of 546 operating rooms into these. In the USA, we had 28 teaching hospitals through a mail-out survey. These housed 339 operating rooms, and compared these with Egyptian setup, where cultural, maintenance, economic setup is totally different, and wanted to see, well, our decisions are similar, is performance similar, and we'll talk about that in a minute. About 207 operating rooms. Data collection by mail survey was difficult in Egypt, so we collected directly data from the Ministry of Health. We looked at certain criteria that were defined in literature: sterile properties, durability, maintenance, aesthetics, comfort, safety, and cost. We looked at these for the 5 aspects of a typical operating room: floor, wall, ceiling, and doors. In regards to sterile properties, we identified, for those who were reviewed, porosity and water tightness, how tight the material is, so that it does not accept molds and so on, surface texture and grooves, amount of size of seams and joints, amount of pitting and cracking, like the things that we see in these pictures. Durability, resistance to impacts, and that happens a lot in hospital setups, resistance to stains, resistance to cleaning agents, abrasion, frequent washing, peeling from the underlayer. Maintenance, we looked at ease of cleaning, frequency of repair and patching, ease of repair and patching, access to electrical and mechanical services behind the surface of the material. Aesthetics, looks, color, clean looking, and attractive appearance. Comfort, underfoot comfort for floors, underfoot warmth for floors as well, and then ease of locating dropped items and glare and light reflection. Safety, we looked at definitely slip resistance, and this is an important aspect in hospital design, fire safety, and a very important aspect, because buildings are almost totally sealed, effect on indoor air quality due to emissions of chemicals coming off of the materials. One last item that we looked at, cost. We did not consider initial cost only. No, we looked also at maintenance cost. Time wasted in maintenance. For an operating room, this is very valuable, because if you shut off an operating room for a day or so, you are losing lots of money. And the useful lifespan of the material, how long would it live and require replacement at a later stage. Let's see some results. Views of the facility managers regarding how important each of those criteria, not yet the performance, but which items they think are more important. So everything was important because we carefully selected our items, but there was a relative importance. 3 of these were more important than the others: sterile properties, being easy to clean and having to provide the infection control requirements. Durability came out to be very important, and safety came out to be a very important issue. Of course, we could not look at that at the general sense, because performance in floors, walls, ceiling, and doors will differ. So we looked carefully in regards to those criteria onto the floors, walls, ceiling, and doors. Came out, for the floors, the 3 same criteria came the same: sterile properties, being able to resist infection risks; durability, being able to resist damage; and also safety came out to be an important aspect. But for walls, other issues came out. Still the previous ones, but maintenance came out to be how to access the support facilities and how to easy for you to maintain the wall surfaces that you have. For the ceiling, 2 different issues came out to be important: cost and safety. And for the doors, because of their mechanical components, the issues like durability and maintenance came out to be important, and of course, definitely safety. We took a closer look at each one of those criteria. For example, here, this is the sterile performance criteria. Which aspect was more important? Was it the surface texture or grooves, or amount of pitting or cracking, or what? So we noticed also that here, for the floors, the porosity, having to absorb water and or other agents, And also amount of pitting and cracking was important. Similar for walls, but for the ceiling and doors, things were a little bit different. In regards to durability, how durable the material is, maintenance and also performance criteria, you find ease of cleaning for the floors, frequency of repair and patching for the walls came out to be important, and for the ceiling, ease of cleaning and access to electrical and mechanical services. So on, I'm not going to bother you much, but it came out to be very interesting that facility managers defined for us what to look for when we select a material. If we look carefully at these criteria and make sure to select the finished materials to satisfy these criteria, then we might be able to achieve better performance of the hospital based on evidence rather than based on intuition. And then second part of the research to see which materials were selected in Egypt and the USA in the sample hospitals. Floors, we found out that sheet vinyl was the most commonly used material in both countries. In Egypt, more dominant, but in the US, there were other materials being used like epoxy terrazzo and ceramic tiles. Ceramic tiles were probably in older types of hospitals because the sample included new and old hospitals, existing hospitals. Wall finishes, we found out that epoxy paints in the general were more dominant in both countries. Epoxy paints was the most important material or more dominant material being used in both countries. But second best was PVC Korean vinyl wall coverings. So we are having two materials being introduced. And then other materials like stainless steel panels, like enamel paints, like porcelain tiles or so on, like marble tiles came out to show out as well in some of the sample hospitals in the USA. Ceiling finishes, drastic difference between the Egyptian and the USA hospitals because of code compliance. The USA hospitals used jointless types of ceilings where you have typically a gypsum board-like type of ceiling, and then you paint it with a certain material like epoxy, acrylic, or enamel paint. While in Egypt, that's not a requirement by code, so tiles for ease of maintenance came out to be more popular, more demanded, and more used, more selected by the designers. And then we said, well, designers showed their interest or showed their preference when they selected these materials. Did these materials perform well as expected by the designers? So we surveyed the facility managers and took the best two materials of each category, and we compared them with the 7 criteria points that we identified for our research. So for example here, this is floors. We compared performance, the actual performance, the views of the facility managers in regards to the actual performance of those two materials, sheet vinyl and epoxy terrazzo. These were the most commonly used two materials in regards to the various criteria. The study shows that, yes, selections of the architects, the designers, were actually performing well in all criteria except in the issue of durability. Epoxy terrazzo performed better in such a category. But the material, the choice was coinciding with actual performance. This did not happen much in walls. If you look at the two most popular materials in walls, you find epoxy paint and the other face materials like PVC, Korean, sheet vinyl, and similar. Epoxy paint, which is most popular and well selected by the architects in our cases, came out to be superior only in maintenance and aesthetics, the looks and in maintenance. While the other material surpassed it in performance in sterile properties, durability, comfort, and safety. So there is a question here, well, did we make good decisions? Same for the ceiling. Paints, which was most popular, came out to be superior in only one criteria or two, while the other criteria, tiles, were more superior. So our observations that, yes, sterile properties, safety, and durability were defined as the most important criteria for floor finishes. The most popular floor finish material, sheet vinyl, was considered superior in all criteria, especially in regards to special properties. Walls, other issues came out to be important, like sterile property, safety, and maintenance. Most popular finish material was epoxy paint, excellent, good performance in regards to sterile properties, comfort, and safety, while the PVC, the second best choice by the designers, was more superior in other criteria issues. Sealing will have two aspects of it. Safety and costs were defined as the most important ones. Tiles proved to be more superior, but they are issues of being jointless, of course, that will have to be addressed. So in general, as a conclusion, there were aspects that we as designers and architects must take account of when we design and select finished materials specifically for this specialized type of space. What was identified for us by the facility managers in this research, that there were three important issues: safety, durability, and sterile properties. Definitely, that's an operating room. And these were followed by maintenance, comfort, and cost. Despite the drastic difference between the technical, economic, and social conditions of Egypt and the USA, the selected finished materials were very similar in both countries. Why? Because these are very specialized spaces. You cannot afford to risk safety of a patient or infection and performance issues. Distinctive requirements of these highly specialized spaces dictate the use of materials of high performance qualities. Designer preferences, as expressed by their selection of materials, did not always provide best performance. They must listen to the facility managers, those who operate, those who do have hands-on experience with the facility itself. We must listen to them and then feed back into the design phase, and that's what evidence design is about. Further actions for me to do: more data collection on the Egyptian survey, update of the US data because it took several years ago, study of the possibility of adoption of a similar survey here in Saudi Arabia, because conditions here are different also from Egypt or the USA. These are the references for the pictures that were put in, and thank you very much.
Time for questions and answers. If anyone has any questions, please. Yes, sir.
Regarding the operation theaters finishings, Dr. Ahmed, we here realize that started to use stainless steel in walls and ceiling as a better solution. From your survey, I think it was not the better solution.
Let me go back to the slide. Being chosen does not mean a better solution. That's my point. Yes, in this survey, we find that in the sampled hospitals, which is a big number, in the USA and Egypt, the frequency of using stainless steel in walls is very little. It was selected too little, right? But we don't know about the performance yet, because it was not used much, so we don't have data about its performance. So you need to qualify understanding of the results here. This is a survey that shows this is how frequently this material was used. Yes, designers in those two countries did not choose stainless steel much. But whether the performance is better or worse, I cannot answer. I don't have data. I am an evidence-based person, so I do not have data yet. So I cannot help you with this decision, except, yes, people did not choose it.
Well, I'm talking about urbanization here in Saudi Arabia and using this stainless steel.
That's why I was saying
it was antibacterial paint for walls and for ceiling, antibacterial paint,
yes.
And now they are changing to stainless steel for roof and walls. Of course, conductive vinyl
The vinyl flooring
used in
is a
all.
common thing that we all use, and it proved also to be very good in performance. I agree with you, but we need to have evidence to say whether it is superior or not. We think it is superior, but there is no evidence yet that it is superior or not. That is why I was saying we need to investigate more, probably here in Saudi Arabia. We need to base our decisions on actual performance, not expected performance. We think they will perform better, but whether after a year or 2 or 3 they will perform better or not, we'll have to do some research to do that. That's what research is about.
Thank you.
Thank you. Any other questions? Yes, sir.
Hello, I'm Jason Shore from HKS out of the States. It's a very good study, Professor Sharif. We appreciate that. May I just add on to the previous question about stainless steel? As a designer, in designing many of these rooms, we are always approached about what is the best. And these studies certainly help us to make those decisions, so we thank you for that. As specific to stainless steel, one of the criteria that I think you might want to potentially focus on a further study is, do these materials offer a certain flexibility or adaptability? For instance, when new equipment is installed, you need to oftentimes retrofit walls, add electrical outlets and such. I would say that intuitively stainless steel would offer us a very good infection control situation, but it would not offer us a very flexible circumstance when you need to renovate or install new equipment in a room. So I think that's a criteria that is important to understand when we talk about the materials in a room, which may be why in many instances the gypsum on the walls is a preferred solution, because it's easy to adapt.
Thank you for pointing that to us. It's an important point, and actually it coincides with one of our criteria, one of the sub-criteria for when we talked about maintenance. Under that heading, maintenance, we added an issue called access to electrical and mechanical services. So it coincides with what you've been saying, and it's already covered in the preferences and responses of the facility managers. You are right. Thank you.
Any other comments or questions? Yes.
Assalamu alaikum.
Assalamu alaikum. My name is Razali Aripin. I just would like to address my question to the first presenter about emergency. I did not see in your presentation, or maybe you can elaborate more on the patient movement during emergency. Or I'm interested to know that is the major issue. How do we transfer a patient from ward to another area? Thank you.
Thank you for the question. Evacuating patients, obviously, is more of an operational aspect. There are lots of operational aspects that were not discussed in today's presentation, and also some of the common emergency mitigation factors, like extra water tanks and so forth. So you are correct. It was not addressed simply because of the these are more of operational.
Any other questions? Yes, sir, over in the corner.
I want to ask about the normal percentage of built-up areas for mechanical and electrical surfaces in the healthcare facilities. What's the normal percentage of the built-up area for these electromechanical surfaces normally?
Sorry, was the question addressed to myself, yes?
I want to ask the percentage of the built-up area specialized for the electrical and mechanical services. Normal percentage of the built-up area.
Oh, right, for mechanical and electrical services. I think that's probably an architect would be able to give a better answer to that in terms of physical area. We tend to focus on how systems work when they're installed. However, in modern hospitals that I've been involved in across the world, it's increased slightly from about 8% to 10%. And the reason for this is to allow more access to the services, and that equipment should be more accessible. This includes underground walkways, tunnels, gantries, and this was really driven by the private-public partnership or private finance initiative back in the late 1990s, where construction companies actually then had to pay for the construction of the hospital and also pay to operate the hospital. And this generated a rethink in the architectural and building services design philosophy. So I think a rough guess would be currently about 10%. Thank you.
Any other questions, comments?
تتقدم شعبة معماري.
السلام عليكم ورحمة الله وبركاته. عندي 3 أسئلة للدكتور أحمد الشريف. أولاً بالنسبة لأبواب غرف العمليات يا دكتور، عايزين المواصفات بتاعتها وتشطيباتها. السؤال الثاني بالنسبة للأماكن اللي بنستخدم فيها الكوندكتيف فينايل. ايه الاماكن اللي بنستخدم فيها الكوندكتيف غير غرف العمليات عشان في خلافات كتيره. السؤال الثالث اللي هي الدهانات الانتي بكتيريا، وازاي اتاكد ان دي دهانات انتي بكتيريا.
Excuse me, I'll have to answer in English because the session is in English. I understood the questions definitely. Doors and conductive tiles, right? And the third one was antibacterial paints, right? How to, let's start with the last one because I'm not going to be able to answer it because today I'm talking about the results of this research, right? So how to inspect and make sure the antibacterial paint is done, maybe after the session in a private talk we can have a discussion on that. But going back to conductive types of flooring, if I take off the hat of the university professor and put the hat of a hospital planner and designer, then I can answer this one. Usually conductive flooring is required only in operating rooms. Other types of spaces could be anti-static, but no need for having the carbon and the conduction properties of a conductive vinyl flooring in other spaces of the hospital. That's my knowledge and preference. But this should be, again, based on evidence, and I don't have the evidence here in this research. In regards to doors, laminated types of doors proven to be more effective. And having durable and easy to clean characteristics would be the essential features of those doors. Stainless steel sliding doors proved also to be very useful and effective in hospital operating rooms, if that would be help you in making your decisions.
بسم الله الرحمن الرحيم. تتقدم شعبة معمارية المباني الصحية بخالص الشكر للسادة المتحدثين ورئيس الجلسة والحضور، والآن يقدم الدكتور زياد السويدان رئيس شعبة معمارية المباني الصحية شهادات شكر وتقدير للسادة المتحدثين ورئيس الجلسة، فليتفضل مشكورا. مستر رياض محفوظ. مستر جريم روبرتسون. بروفيسور أحمد شريف. واخيرا مستر وين بيرفورد. نشكر السادة الحضور، والآن بريك، و next session will be at 10:45.